Let's say that our world is a place where scientific ideas are like shooting stars. They shine brightly in the night sky of human curiosity, but not all of them stand the test of time. Some theories, such as that of Phlogiston, which dominated the 18th century, proposed that something mysterious was released when something burned. After all, thanks to the brilliant Antoine Lavoisier, we discovered that heat and combustion are actually the result of chemical reactions between elements. Now think of the Big Bang, the explosive theory that suggests our universe began as an infinitely small, hot dot and expanded into the vast cosmic structures we see today. Competing with it was the steady-state theory, which envisioned an eternally unchanged universe, where matter is constantly created to keep everything the same. Today, while the world continues to debate, scientists and mathematicians are immersed in even more complex theories, such as string theory, M theory. In fact, what they are trying to do is nothing less than unify the great theories of physics, fitting everything from gravity to quantum mysteries into a single cosmic puzzle. It's incredible that, although we may be just over 1.5 meters tall, our eyes can focus on things as tiny as the insects crawling around us. Now imagine zooming out even further into the molecules and atoms that make up everything around us. Here we're talking about distances of less than 1/1000th of a meter. Yes, this is where quantum mechanics begins to rule. What if I told you that if we looked around in a tiny cube of this size, we'd find more of these cubes inside us than there are stars in the observable universe? But we don't stop there. We go deeper to the heart of atoms, where we find the nucleus, a place where the distance is about 100,000 times smaller than the size of the atom. And inside this nucleus, protons and neutrons, tiny clusters of quarks, all dancing to the rhythm of the strong nuclear force. Particle colliders, these giants of science, are our super microscopes, allowing us to plumb these depths even further, until we reach the realm of particle physics. But wait, there's more. On the scale of 1,000,000 billionths of a picometer, quantum gravity takes over. And this is where we enter the territory of string theory. And speaking of string theory, did you know that this revolutionary idea didn't start out as a fundamental theory of nature, but as an attempt to explain the strong nuclear force in the hot summer of 1968? It began by trying to describe how protons and neutrons stick together. However, string theory faced its own set of challenges and was almost discarded, only to be resurrected later to explain nothing less than quantum gravity. M theory, on the other hand, unlike the 5-string theories known at the time, proposes a reality made up of 11 dimensions and not just 10. Edward Witten, a physicist who initially studied history, ended up becoming a bridge between theoretical physics and pure mathematics. With a unique ability to speak the languages of both disciplines, he was instrumental in rekindling the relationship between these two fields. Imagine, he was so influential that he became the first physicist to win the Fields Medal, considered the Nobel Prize for mathematics. In M theory, an idea from theoretical physics, the main elements are called branes. Imagine branes as sheets that can have several dimensions, not just the 3 we're used to: height, width, and depth. These branes can exist in spaces with more than 3 dimensions, some that we can't even perceive or imagine. Sometimes, these branes can wrap around each other so tightly that they look like lines or ropes. It's as if you took a large sheet of paper and rolled it into a thin tube. Seen from a distance, this rolled-up sheet can look like nothing more than a line. The fascinating idea here is that the universe we live in, with its stars and galaxies, may be just a surface or layer within a much larger and more complex space. Just as the page of a book is part of a stack of many pages, our universe may be just one of many layers within a larger book, with many pages or dimensions that we don't see. Therefore, according to M theory, what we experience as our 3-dimensional universe may be just one of several forms that the universe can take, depending on how these branes are configured in higher dimensions. This suggests that there is much more to reality than we can observe or understand from our limited perspective. All forces such as electromagnetism, which makes your cell phone work, and the nuclear force, which keeps the sun shining, are like waves or vibrations that occur on the surface of this brane. Imagine that these forces are like the waves you see on the surface of a lake. But what about gravity? Here things get interesting. Gravity is like the disobedient student in the class. It doesn't just stay on the surface of the pond. Instead, it spreads across all dimensions, even the ones we don't perceive directly. This helps explain why gravity is so weak compared to other forces. For example, it's easy for you to lift a pen with your finger, defying the gravity of the entire Earth, which is trying to pull the pen down. But let's make all this even more interesting. Imagine if our universe had started with a big collision, a collision between two of those gigantic branes that may have triggered the Big Bang. This is the so-called ekpyrotic scenario. This collision could have created small wrinkles or marks in our brain, which, with the help of gravity, grew over billions of years to form the galaxies and galaxy clusters we see in the night sky. Theoretical physics, my friends, is a challenging game even on the best of days, and especially when we venture beyond experimental evidence. We are on a lonely path, exploring theories that we cannot directly test at the moment. To put it in perspective, even the mighty Large Hadron Collider, that marvel of modern technology, still comes nowhere near the energies needed to prove the scales of quantum gravity. And if you're new here, you may have asked yourself, but what is the Large Hadron Collider? The Large Hadron Collider, LHC, is the world's largest and most powerful particle accelerator, located at the European Organization for Nuclear Research, CERN, near Geneva, Switzerland. Built to circulate subatomic particles, such as protons, at extremely high speeds in a circular tunnel 27 kilometers in circumference, the LHC allows these particles to collide. The collisions generate a vast array of other subatomic particles that are analyzed by scientists to study the foundations of matter and the fundamental forces of nature, helping to answer big questions about the origin of the universe and other fundamental properties of physics, such as the existence of the Higgs boson, often called the God particle, which was confirmed by the LHC in 2012. But how can we be sure that our equations aren't just scribbles on a blackboard? This is where Maldaceno's duality comes in, a concept in theoretical physics that proposes something fascinating. Theories that seem completely different on the surface may actually be just two different ways of describing the same reality. Imagine you have two different descriptions of an object, such as an elephant. One person, looking only at the trunk, might think that the elephant is like a snake. Another person, touching only the leg, might think it looks more like a tree. Each of these descriptions is true from the point of view of the beholder, but none of them tells the whole story of what an elephant really is. It's as if two people were describing different parts of the same elephant without knowing they were talking about the same animal. This is the dilemma when we talk about scientific theories, especially in fields like theoretical physics, where we often can't directly test our theories with experiments. How then can we know if a theory is really valid or just good math that doesn't correspond to reality? Maldaceno's duality tells us that, in certain contexts, two theories that seem to have no relation to each other, one describing forces and particles in a three-dimensional universe, and the other describing gravity in a universe with more dimensions, can surprisingly be just two views of the same phenomenon. So this duality helps us to understand that the complexities of our theories can be reconciled and unified in ways we didn't initially imagine. This is crucial in helping us to distinguish which theories really do have the capacity to describe the universe correctly. Thanks for sticking around. Leave more suggestions for topics in the comments. See you next time.